Thank you all for coming and having me here. So I'm Longqi. I'm coming from Cornell University. Actually, I spent 4 years of my 5 years of PhD at Cornell Tech, which is our new campus in New York City that is focusing on everything about digital and computing technologies. So in this talk, I'm going to talk about my thesis research on how can we build user-centric recommendation models and systems. So recommendation systems are really everywhere. You know, starting from the morning that you get out of bed, you check your social media and news feed, and when you commute to work, you listen to music and podcasts from Spotify. And during daytime, your email clients tells you which email you should pay attention to. And after work, you are trying to find a restaurant on Yelp and doing some online shopping on Amazon and FreshDirect. And basically, all of the content that you see on these platforms are selected by recommendation systems from millions or billions of information items. And in fact, these days, even when you're applying for jobs or taking online courses, the job posts and the course suggestions that you see are also selected by recommendation systems. So essentially, you are interacting with recommendation systems every day and every hour. And these systems have profound impact on people and our society. So my research, generally speaking, is about how can we design, build, and understand recommendation systems for individuals. And this is about how can we fundamentally increase recommendation systems' utility for individual users and empower their work and life in the short and long term. And when we put user at the nexus of recommendation systems, it brings very exciting research challenges and opportunities in designing new recommendation algorithms, building novel systems, and having real-world impacts through field experiments. But before I talk about these, I want to spend a few slides showing you why today's systems are not built for individuals yet. So most of the existing recommendation systems these days model users' preferences using people's positive feedback signals, meaning the positive actions that users took on items. For example, a user click on a tweet or a Facebook post, purchase a product, view an article or web page, or even subscribe to a podcast channel. And in the abstract level, these kind of signals provided us with a binary indication of user preferences, with the observed being like and unobserved being unknown. And in recommendation system literature, these kind of signals are also referred to as implicit feedback, which I will use interchangeably with positive feedback in the rest of this talk. And with such a feedback signal, what recommendation system is basically doing is that it takes a user's positive feedback history as input and outputs a ranked list of items. And let me make this more concrete. So let's say, now we are interested in recommending 4 books. And we observe that the user read the book Deep Learning and the Thinking Fast and Slow. And under this scenario, what recommendation system need to do is to take the 2 books that the user read as inputs and then generate a ranked list of books that the user has never read before. And in this particular scenario, basically the system predicts that the user liked the book of Y the most, followed by the Linux Pocket Guide and Harry Potter. And this kind of implicit feedback has been widely used in the recommendation system literature, from the traditional matrix factorization-based approaches to the most recent deep learning-based approaches, and including many papers that I cite in these slides that have significantly influenced and inspired my work. However, if we think carefully about this design paradigm of recommendation systems, it has a very strong assumption behind. Basically, a user's preferences equal to their implicit feedback. And I want to argue that this is a fundamentally biased and incomplete view of user preferences. And this is biased because the implicit feedback that these systems observe are biased. And users can only interact with the things that they were exposed to. In other words, exposure is a very significant confounding factor that modulates the implicit feedback. And in reality, users' exposure is typically very hard to observe because it can be determined by many biased factors, including what the current production recommendation system show to the user, what's the business logic of the service provider, and sometimes even the screen size of the user's devices can affect their exposure. And in fact, as end users, we constantly encounter these kind of biases in our daily interactions with recommendation systems. For example, you might watch a video about Super Bowl just because YouTube recommends this video to you. And although you're not more interested in Super Bowl than others, after you watch this video, your YouTube recommendations will be overly populated by content relevant to Super Bowl. And you might have bought the shoes just because Amazon was promoting it on Black Friday. And although you're not that interested in shoes and definitely not more shoes, now a significant portion of your recommendations are not about shoes, no matter where you go on the internet. And in addition to being biased, these systems also have an incomplete view of user preferences. And this is incomplete because, first of all, the traditional approaches requires a significant amount of implicit feedback in order to build a relatively complete user profile. And in domains where implicit feedback is sparse, or for cold start users, these kind of profiling tends to be very incomplete. And more importantly, implicit feedback does not reflect the aspirational aspect of user preferences. And here I use aspirational preferences refer to what people aspire to have or aspire to be, which is about futures and goals, and it's different from people's current preferences that captures what people's preferences right now. For example, if you ask people what they want to eat in the long run, they may say salad because they want to stay healthy. But when they go out to the restaurant, they may choose burgers and fries because these are what they're interested in right now. And if you ask graduate students what they want to watch on YouTube, they may say, lectures and tutorials, but in reality, they watch a lot of entertainment videos. So it's very important to understand people's aspirational preferences because eventually we want to build a recommendation system that help people to achieve their better self. So all of the limitations that I talk about so far really tells us that we need to rethink our current paradigm of preference modeling. User preferences does not equal to their implicit feedback, and optimizing for implicit feedback is just a tool for us to build better systems for users, and that itself is never the goal. And in other words, we need user-centric recommendation system and properly address the bias and incompleteness problem that I mentioned earlier. So my thesis research contributes three building blocks for user-centric recommendation systems. First is about how can we model and reduce the biases in implicit feedback. And second is about how can we leverage broader data sources beyond implicit feedback to more comprehensively profile users. And third is about how can we build interactive systems that can learn about user preferences beyond offline data. Dan, you have a question? Yes.
So I am parsing the whole beginning of your talk in terms of reinforcement learning and thinking about what is the reward signal that the recommender system is taking. And obviously one reward signal that has some benefits and some weaknesses are measures like user engagement, how many times they click, how many ads I'm able to show them. If that's not the end goal, what is the end goal?
That's the research question. Actually, so I will talk about some of different kind of objective function that we can use, but not in the context of reinforcement learning. So it's more like how can we train a model using like offline behavioral data. It's more like it's not an interactive setting. So in the second example, I will talk about an interactive setting, but that is not a reinforcement learning kind of a scenario. But I think one of the most important challenges here is to figure out what's the best objective function, and in the case that you mentioned is what's the best reward function.
Okay, thanks.
Yeah, but I don't think we have the answers yet for that particular question. Cool. Yeah. So and in addition to these three things, during my PhD, I've also built tools that can help to generalize or adapt solutions that we develop for specific domains to different application scenarios. And in comparison, if you look at the existing literature, it mostly builds recommendation systems directly using implicit feedback. And although it's well known that users' ratings are biased, it is unclear and unknown for implicit feedback. And in terms of the research methodologies, my work has tackled all three important aspects of recommendation systems. So I built novel recommendation algorithms, deploy real-world systems, and conduct field experiments to understand what's the real-world impacts of recommendation systems and personalization. And my work has also spanned across many domains, as shown in this slide. And also over my PhD, I've been very fortunate to collaborate with people broadly in different fields, including people in the broad computing fields, from computer vision to systems, social computing, and human-computer interaction. And I've also collaborated with people from other disciplines, such as behavior science and medical school. And I'm not going to talk about all of these in this talk. And instead, in this talk, I'm going to walk you through two example projects, showing you how we can reduce and model the biases in implicit feedback, and how can we build interactive systems that can address the limitations of the offline data. So before I jump into formalize the biases and design of our approach, I want to give you some biases of where does this kind of biases come from. So let's start from the Super Bowl example that I talked about earlier. So it was Super Bowl season, but there are many people who are not that into Super Bowl but watch a lot of Super Bowl video. Why? Because when they open the YouTube app, these videos are always their top recommendations. And yes, these people are interested in Super Bowl, but it does not mean that they are more interested in Super Bowl than others. In fact, if we look at this person's watch history, we can actually see that this person is also interested in startup, music, art, and game. And what is happening here is that users' preferences are skewed when we look at their implicit feedback signals. And in this particular example, users' preferences for Super Bowl is significantly amplified because of the external seasonal factors that are reflected in the production recommendation systems. And unfortunately, the current paradigm of training and evaluating recommendation systems puts equal weights on every single example that the system observes. And what will happen is that the recommendation system will put much more weights on recommending content that are relevant to users' interest in Super Bowl and overlook others. And this is where the biases come from. So how can we address this problem? Our idea is that when we train at evaluation or evaluating recommendation systems, we need to somehow put weights to correct this kind of unbalanced distribution of implicit feedback. And in this particular example, we would want that in our loss function or in our evaluation metric, we can multiply the Super Bowl related signals by something like a quarter. And we roughly know these numbers here because we know users' true preferences in this particular context. But in reality, we'll never know users' true preferences. So the main contribution of our work here is to fundamentally model the biases and derive a principled and practical way to calculate these weights. So next, I'm going to step into details and talk about our approach. And first, I would like to define some notations that I will use in this presentation. First, I define a set of items that users truly prefer as S. And this set is not observed in reality. And then I use the set S star to represent the set of items that we observe in implicit feedback. And according to the definition of implicit feedback, S star is naturally a subset of S. And this set is observed in reality. And then we can think of the task of recommendation as predicting a real valued vector, z hat, that has the dimensionality n, where n is the number of items. And then each dimension in z hat represents how much the system predicts a user-liked item. The higher the value, the higher the preferences. And then the task that we care about is to measure to what extent z hat captures users' true preferences. And in other words, we want to derive some kind of performance measure R that will output higher value for z hat that are closer to users' preferences. And during training, you can think of R as your loss function. And during evaluation, R is basically your evaluation metric. And in recommendation systems, these two things are mostly consistent in different kind of approaches. So for the simplicity of this presentation, I'm not going to distinguish them here. So now let me show you how the current approach works. So given the z hat, and
I'm sorry, I'm missing what R is.
so R is basically, you can think of it's a loss function or your evaluation metric.
But how are you quantifying that?
So basically, you can think of so z hat is basically you can think of that as the output of the model, and then the R will basically calculate some kind of like how well the performance of this current recommendation is, and give you a number. And then the function R is completely differentiable, and in most of the deep learning based cases, then you can just calculate the gradients and such. I will show some concrete example later. Yeah.
To what extent is it a problem that, so you talked about implicit feedback, but people also have implicit preferences, which they're not going to give you such that they're truly observed. So do you have any thoughts about like how much that impacts this way of modeling, this problem? Because I see that it also happens the other way. Like for instance, maybe I'm from the UK, so I don't talk very much about American football. Somehow on YouTube I do occasionally watch videos about American football. So in that sense, my preference is kind of implicit and actually well modeled by implicit feedback, and poorly modeled by my own like reported preferences.
Yes. So I don't really understand what you mean by reported preferences. So
in this case, you have a set of true user preferences, but it's possibly the case that those preferences suffer a reporting bias.
Oh, the set S will never observe in reality. So basically, like we are not going to ask users about the set S. So this is basically we assume there's a hidden, user preferences out there, and that's the goal. Like that's something that we want to estimate, but we are not going to like ask users like what's your S. So that will never happen. Yeah.
So I guess I'm still a little bit confused because the idea that we can model a user or imagine the true model of a user being some set of items that they like seems really impoverished for me. And furthermore, that the fact that S star is a subset of S also seems to be wrong. It seems like there's some things I like more than other things. It's not like there's a set of things I like and a set of things I don't like. And I might actually click on something that I really don't like at all because everything else looked even worse. So
yeah.
the
So
model seems kind of weird to have it be binary, and to the assumption that the implicit feedback actually has any resemblance without context seems hard to get to.
yeah. So this is a very good question, and I think so. Implicit feedback is definitely not perfect to represent user preferences. Like for example, if we can ask people to do 1 to 5 ratings, then that is a better kind of representations of users' preferences. And as you mentioned, when people click on or consume something, that it does not really mean that the user just like this item. So this is something, like I guess this is the best we can do in most of the the content platforms. So if you don't want to actively asking users about their preferences, because if you want to just model their preferences from their the implicit signals, then there's always noise there. Actually, so in our model, we didn't consider these kind of noises. So there's a certain percentage of items that user click are not necessarily the things that they like. But some other work actually show that even if you sort of model that kind of biases, that it will not like affect the model of affect the outcome of our model, because that will cancel out at the end. But this is a very good observation. But so this is just like we sort of follow the the tradition of how can we leverage implicit feedback, and there's a very strong assumption here. Basically, if we observe implicit feedback from user, then we sort of think that the user like this particular item. But like I guess this is just the best we can do. There's
I'm done for now.
okay.
Just to clarify, say that S is unobserved,
Mm.
are you saying that you're going to treat this as like a latent thing that you'll never be able to observe, or
Yeah.
is this like it's unobserved for now, but we are capable of actually like collecting gold or true data from the user somehow for S?
We cannot collect a perfect S from user, but there are some ways that we can collect, like estimate S from, like basically show user randomly set of things and then ask them to give feedback. Then we can sort of estimate what S is, but we'll never.
You could reasonably actually collect.
Yeah, we can reasonably, actually estimate or collect. But in the real world systems, it's very hard to collect this. You need to, actively engage users for that. Okay. Cool. So what's any question from the remote? Okay. Anyway, I'll just go on. So yeah, as I defined before, so given z hat and a star, what the current approach is basically doing is that for every item that we observe implicit feedback, it's basically for every I in this set S star, we will feed that into a function f that will basically output higher value for items if item I is ranked higher according to z hat. And what this is basically saying is that we want the recommendation system to output higher values for items that we observe implicit feedback. And this is what the f basically is representing. And after we calculate this item-wise evaluation metric, then we basically directly take an average over the S star. And this is what the current approach would do. And this is kind of directly average is the the uniform weights problem that I talked about earlier, and it's the source of the biases. And ideally, this is something that we want. So we want to take an average over the set S instead of S star because, well, S star is biased, but S is not. So in order to sort of understand what the biases come from, we need to somehow bridge the gap between the current approach and the ideal performance. So essentially, we would hope that we can represent the current approach by the set S instead of S star so that we can bridge these two things together. And our idea is to think about S star as a randomly sampled subset of S. So basically, for each item, we use a Bernoulli distributed random variable to model whether or not we observe implicit feedback, with 1 being observed and 0 otherwise. And the probability of observation is pi. And then with such a probabilistic view, then we can rewrite the current approach using an average over the set S with the item-wise evaluation multiplied by O. And it's easy to show its equivalence because the unobserved things are canceled out by setting O to 0. And what this equation, the nice thing about this equation is that now we can show that the biases fundamentally comes from the fact that the expectation of the current performance measure is not equal to the true performance. And ideally, we want a performance measure that is unbiased, or it is consistent, meaning it converges in probability to the true performance. And in order to do this, we leverage the self-normalized inverse propensity scoring technique from counterfactual reasoning to derive a consistent performance measure. So the basic idea here is to weight the item-wise evaluation by the inverse probability or propensity of observing this particular implicit feedback, and then normalize them by the sum of the inverse propensities. And what this equation is basically saying is that the weights that we are thinking about to assign to each Super Bowl video earlier should be proportional to the inverse propensities. So now the question becomes, how can we estimate the propensity values? So unfortunately, perfectly estimating PI is intractable because, as I mentioned earlier, there are so many hidden factors that can potentially affect the propensity values. But the good news is that I will show later in this presentation, we don't actually need a perfect estimation in order to do a better job. In fact, a rough estimation can already significantly reduce the biases of the current approach. So I'm going to talk about this estimation in the standard recommendation scenario where we only have implicit feedback data. And this is one of the most generally applicable and hardest scenario because we don't have any site information to use in this particular estimation. Specifically, we leveraged item popularity information that is pervasively available on these platforms. And as shown in this graph shows a typical long-tail popularity distribution that one would observe on any kind of content platforms. And the y-axis here is item popularity, and x-axis are items sorted by popularity. And the intuition here is that recommendation systems tend to recommend more popular items than long-tail ones. Therefore, the items that are closer to the y-axis, that is the popular items, they tend to have higher propensity, and propensity for the items that are farther away are lower. Yes?
Popularity in this case is some statistic computer based on whatever the implicit feedback is?
Yeah, it can be like directly computed from the implicit feedback, or it can be like determined by some kind of platform-specific metrics. So basically, it basically models like how frequent are the current recommendation system recommend different items. Okay, so then based on this assumption, we then model the propensity value as follows. First, we disentangle this event of observation into two consecutive and independent phases, where the select phase, where the system chooses the items to present to the user, and the interact phase, where the user interacts with items that are presented. And these two phases happens with certain probability, and if these both phases happen, then we observe implicit feedback. And then we use the power law distribution to model the select probability to see why this is the case. Here I train 4 different recommendation algorithms using an implicit feedback data set collected from Tradesy, which is one of the e-commerce websites. And then I visualize the relationship between the number of times that items are presented, that is the y-axis, and the item popularity, that is the x-axis. And according to the definition, so select probability is proportional to the y-axis. And note that both x and y-axis are log-scaled in this particular graph. And all these lines here are almost linear, means that like regardless of the recommendation algorithm, the behavior of these kind of algorithms can be approximated by power law distributions. And at last, we assume that the propensity values are user independent because we want to get enough samples to do the estimation, and the number of items that a single user interacted with tend to be very small. And after doing some linear algebra, then we can actually show that the propensity value can be estimated by some polynomial function over the item popularity. And note that there are many assumptions that we make here can be actually be relaxed in reality. For example, if we are in industry, we have access to our production recommendation system, then we can build an accurate model. We actually know what the selection probability is. We don't need to estimate it. And also, if in the system we have access to some user demographic information or user site information, then we can build a user dependent model using some kind of regression. Okay, so now let's zoom out from the details and talk about how can we evaluate this kind of approach. So to do the evaluation, we need to ask users to evaluate a randomly set of items because we want to get their true preferences. And in order to do this, we leverage a data set that came from Yahoo Music, and it contains a natural set with the implicit feedback that users give through natural interactions. Therefore, this set is biased. And it also contains an unbiased set where a set of users are asked to give feedback to a randomly select set of music and choose the ones they like. Therefore, on this unbiased set, we can actually estimate what users' true preferences are. And for each recommendation algorithm, we calculate we apply the current performance measure an hour. Yes?
With the unbiased data set, I'm not familiar with it. So I can imagine that if you do it uniformly random.
Uniformly random.
Pretty much just say no to most of things. How do they actually?
So basically, the set of music is not that many. So it's not like millions of music. I think it's like 1,000 of music. So the item pool is not like in the scale of millions.
Are they like popular music around some time?
That I don't remember. They describe in their data set like how do they select a set of music, but in both set the music are sort of not the all of the music in their database. It's a subset of them. Any other question? Okay, cool. And then so basically on the natural data set, we apply the current performance measure, the current approach, as well as our debiased measure. And on the unbiased set, as I mentioned earlier, we can calculate what's the ideal performance of the recommendation system because we can estimate users' true preferences.
I'm trying to understand that too. I'm trying to understand what the data actually looks like and what the ideal performance is. In particular, imagine as a user, if I'm given a whole bunch of random music, and in fact I don't like most of it, that when I hear something that I even remotely like, I might be so happy that I say I like something.
Yeah.
When if it was in the context of music I really liked, I would say I didn't like that thing.
Okay.
So I don't know if that phenomenon occurs here, and obviously it must depend on what percentage of things I like, but I'm just trying to understand what we're going to be able to learn here.
Yeah, so when collecting the unbiased data set, they actually ask users to do 1 to 5 absolute ratings. It's not do relative comparisons. So basically, for every single music, they need to do 1 to 5. The like scale ratings. So I guess the choice set problem might be less of a problem in that case, but.
Right, but people aren't rational, and there is no absolute ranking for what one likes about a song. So
yeah, this is definitely a limitation. I guess in all of the recommendation things that you can reasonably evaluate, like there's always this, the choice set problem. Like what are the options? What are the other options in your choice set, and that will affect your preferences for that particular item. That is like mostly ignored in all of the literature. So this is something that I think is another kind of bias that we need to address in the future. But in this work, we don't really consider that factor because it's very hard to measure because we don't really know the ground truth.
It's true, but if you did learn 2 different recommenders, you could play a stream of music to the user and alternate selections from the 2 different recommenders and see which ones were actually most likely appreciated, right?
Yeah, so in the next project, we're actually doing this. Because this is offline data set, we don't really have control over the data that is already collected, but in the interactive system that we develop, we actually do this approach. Yeah. Cool. Great. So on this data set, we evaluate 4 widely used recommendation algorithms. And then we calculate the mean absolute difference between the estimated performance and the true performance. We actually find that the current approach is significantly biased with the error reaching almost 0.4. And note that the random guess only produces error of 0.5. And this phenomenon is not new because in the industry, if you ask people about offline evaluation of recommendation system, they will say, it is not that consistent with online performance. And this particular phenomenon is we in this particular work, we basically just quantified the current approach is significantly biased. And our approach is still not perfect, but it can significantly reduce 1/3 of the biases. So that's why, when I said earlier in this talk, we don't really need a perfect estimation in order to do a better job. But there is still a significant error there that we need to do, better estimation of the propensities and such for the future work. And in fact, this is not just something that we did in the offline data set. So there is some concurrent and follow-up work from Spotify research actually deployed this solution in the production system, and they find that this is a much better representation of recommendation performance than the current approach, although it's not perfect. Okay. Great. So now I've shown you how can we use implicit feedback and debias them to learn sort of debiased user preferences. But any kind of implicit feedback or offline data alone, there are many limitations, as some of the questions that Dan raised. So next, I'm going to show you how we can build interactive systems to learn user preferences, broader user preferences that are not reflected in the offline data set that we collected. So specifically, I'm going to walk you through a recommendation system that we built that recommends recipes not only cater to users' food preferences, but also satisfy their nutritional aspirations. And building such a system really requires to go beyond offline data, because the current offline data about users' food consumption mostly comes from food journaling. And the current journaling system typically requires users to manually input ingredients or the nutrients they consumed, and it's very cumbersome for users to do so. And as a result, the offline data in this particular domain is very sparse. And also, it does not reflect people's nutritional goals, which are very important in food recommendations, because we don't want to recommend food that people are obsessed with but divergent from their health objectives. And the system that we built is called Yummy, which contains three main components: an interactive preference elicitation component that learns about people's food preferences interactively, and a survey component that collects people's nutritional aspirations, and the re-ranking component that combines both users' preferences and generate appropriate recommendations. So I will start from the interactive preference elicitation component. So in this particular example, I will continue to use the same definition of recommendation systems as in the previous project. That being said, we are interested in construct a real-valued vector z hat that has the dimensionality n, where n now denotes the number of candidate recipes in our database. And this kind of interactive setting might remind you of active learning that is commonly used to collect labels for machine learning algorithms. But I want to argue that the system we are trying to build is very different from the active learning algorithms, no matter if it's active learning for classification or active learning for ranking. On the one hand, active classification algorithms often choose the items that are close to the decision boundary to elicit labels. And under this scenario of preference elicitation, what will happen is that these items are the items that people are especially unsure about whether or not they're interested in them. Therefore, the collected labels can be meaningless, and it also degrades user experiences. And also, the active ranking algorithms are mostly optimized for the total rank of items. But in recommendation systems, we mostly only care about top-ranked items because these are the ones that get presented to the user. And in other words, the comparisons between the long-tail items are likely to be wasted in this particular context. So just to consolidate, there are two main challenges that we need to address in building such a recommendation system. First is to address the uncertainty of the user preferences and provide good user experience. And second is to develop systems that are sample efficient, because we are not going to have an abundance of data points to learn preferences from. And to address the first challenge, we develop a system that is a visual pairwise comparison-based system. The users are asked to do a series of pairwise comparisons of food photos, and choose the ones that she likes more. And compared to asking people to do classify each item into like or dislike, this kind of pairwise comparison approach has been shown to be a much easier and reliable task, because users do not need to give an absolute score of their preferences. And also, the food photos can help people to make distinctions, because a picture is worth 1,000 words, and also people have apparent desire to engage with visually appealing content. And built on such a system design, we then develop an interactive learning algorithm that leverages the visual similarities between recipes. And the reason why we leverage visual similarity is that it captures many aspects of recipes that are not reflected in the ingredients level. For example, its cooking style and its cuisine. And specifically, the algorithm maintains a uniformly initialized user state, z hat, and has two alternating algorithm stages. The user state update stage, where the system updates user states based on user selections, and the image selection stage, where the system chooses which pair of images to present to the users to compare based on the current user state. Yes.
So I guess specifically for the image selection thing, is the objective to select, for example, for the pizza thing, images of two pizzas for which there's only one ingredient that's different? Because then you're trying to kind of elicit that, oh yeah, I don't like that ingredient, or is it like, are you allowing for like 5 things to be different? In which case, I don't really know if I, as a user, can really.
I will go into that later when I describe how we do the image selection. But we don't really do the ingredients thing, like the specific ingredients thing. We mostly use the visual similarity to do the selection. But I will go into the detailed algorithm. Okay, so for the user state update, when a user selects an item against the other, we convert that into a labeling process where the selected item is treated as label +1, and the other item is treated as the label -1. And then we design a regularized label propagation process that propagates the labels to similar food items in our database. And in this particular example, the label +1 is propagated to similar noodles, and the label -1 is propagated to similar burgers. And the amount of propagation here is determined by solving a regularized optimization problem. I'm not going into the details of this optimization problem, but the basic idea is to balance the smoothness and fitness of the propagation. And eventually, the propagated amount is equal to some kind of a Gaussian-like cutoff Gaussian-like function with the feature representation, with the Euclidean distances measured using some feature representations of the recipes. So as you can see here, the critical components actually derive this function g that projects recipes into an embedding space where we can use Euclidean distances to measure similarities. And in other words, in this space, we want the similar food items to be close to each other and dissimilar ones to be farther away. And we conduct such a projection by using a deep convolutional neural network. And we train this network using multitask training over a large-scale food data set. So specifically, we first develop a network to classify the categories of food images, as shown in this slide. And then we use the same network to build a Siamese network to directly learn the distance metric. And what Siamese network is basically saying is that it has 2 identical networks with shared weights. And it takes a pair of images at a time. And for the recipes that are from the same category, the network learns to minimize the learned Euclidean distances. And for the recipes that are from the different category, the network learns to push the Euclidean distances above a threshold m. And by training this network using 2 tasks at the same time, it gives us a very nice embedding that characterizes the similarities between food recipes. And eventually, this is the embedding that we get. So as you can see here, similar food items are close to each other, and dissimilar ones are farther away. And when we developed this model, we also quantitatively evaluated using a food image classification task. And we are able to show that our approach is able to outperform most of the state-of-the-art models at the time that our paper was published. So after the propagated amount is calculated, then we update each dimension in z hat at time t by weighting it with an exponential. And the exponent here is composed of the propagated value v over the current value in z hat. And when v is positive, then z hat is amplified. And if v is negative, then z hat is reduced. And we can think of this division by z hat as some kind of importance sampling, because z hat correlates with the probability that each item is selected to present to the user. And this kind of weighting can correct the bias that certain items are more often compared than others. And for people who are familiar with multi-arm bandits, this approach is inspired by the EXP3 algorithm used in that setting. And then after the user state is updated, the next question is how can we select a pair of images for users to compare next? And in order to do this, we develop a method that is optimized for the top-ranked items and that at the same time explored unknown content space. So specifically, the idea is to keep track of the items or the recipes that have already been explored or propagated. And then randomly select one item from the set that the system predicts that the user like, so that the system can maintain a very good set of top-ranked items. And the other item from the unexplored content space, so that the system can explore the unknown user preferences. And then to evaluate how well our preference elicitation captures users' preferences, we conduct an online users testing with 227 participants. So after the user finished the learning process, we additionally collect 10 rounds of pairwise comparisons and treat them as the testing ground truths. And in other words, each learned model needs to do 10 rounds of pairwise comparisons and 10 rounds of binary classifications, basically. And in this particular scenario, random guess produce an accuracy of 50%. And we compare our approach to some of the competitive baseline approach, including the traditional active learning kind of based approach. So we find that best baseline approach achieves a 66% accuracy, while our system achieves 78%, which is significantly better in terms of these binary classifications. And we find that in order to achieve this 78% accuracy, users only need to go through 10 to 15 rounds of pairwise comparisons. And that's amount to about like 50 seconds in total. So now I've shown you how we can learn users' food preferences interactively. Next, I'm going to briefly go through how can we collect people's nutritional aspirations and conduct some kind of re-ranking to generate recommendations. So to collect people's nutritional aspirations, we present a simple survey as shown in this slide. And basically, each participant was asked to choose reduce, maintain, or increase for calorie, protein, and fat. And this kind of survey design is grounded on the common ways that people set their health goals in the commercial or the clinically validated applications. And after we collect both the aspirational and users' current food preferences, we then generate the recommendations as following. First, we sort recipes based on their appropriateness for people's nutritional aspirations. And this is basically the candidate generation phase. And then we take the top 10% of most appropriate recipes and then re-rank them by the user's preferences Z hat learned from the interactive system. And then the re-ranked list is treated as the top-end recommendations. So to evaluate an end-to-end system, we conduct a lab study with 60 participants. So each participant was asked to use all the 3 components of our system. And at the end of the learning process, they were presented with a shuffled list of recipes that are recommended by 2 recommenders. So one is our system, and the other is the clinical baseline that only considers people's nutritional aspirations. And for each recipes here, the users is asked to drag into yummy or no way. So that basically gives you a direct indication of users' preferences. And then we use this kind of a study to answer 2 evaluation questions. First, do users like our recipe recommendations? Yes.
Is it a binary recommendation?
Yeah. So the user will basically, for each recipe that get recommended, it will.
So it's not a slider.
It's not a slider. Oh, the slider is basically there are many more recipes.
Okay. Yeah. I thought it was a slider.
No. And each recipe is recommended one of the 2, system. Okay.
So in both cases, you were sorting by nutritional preferences and then filtering based on the recommender, or you were doing that for your system, and I wasn't sure what the baseline was doing.
So the baseline is basically only do the nutritional part, don't do there's no preferences part.
And so you weren't using the baseline preference algorithm to
No.
there?
No. It's basically, it's one of the clinical baseline where, you only consider about people's nutritional goals and don't know about their preferences. And this is what many nutritionists or doctors do when patients come to their office. So that's the rationale behind the baseline. Okay. So for the first question, we find that over 72% of the recommendations from Yummy are liked by the users or the participants. But when it comes to the nutritional only baseline, the acceptance rate is much lower, only around 50%. And for the second question of how will our recommendations guide users towards their aspirations, Here I'm going to go through one set of results here. So let's take the users who want to reduce fat as an example. And in this figure, I'm going to show the average amount of fat in different set of meals. And first, let's normalize the people's average amount of fat in people's favorite meals to be 1. That is the orange bar here. And then if we look at the clinical baseline or the nutrient-only approach, the blue bar here, it is much lower, which means the current approach is very effective in helping people achieve their nutritional goals. And if we look at the recommendations from Yummy, it is almost equally well, performs almost equally well nutritional-wise. And what this is basically saying is that considering users' preferences does not need to sacrifice the performance in the nutritional side. And our system is able to achieve the best of both worlds. It generates recommendations that are liked by the user and at the same time satisfy their nutritional goals. And we find the same trends in other aspirational goals, not only in reduced fat, but also in reduced calories, increased proteins, and many others. And I'm not going to go through all the results here. Since our paper was published, this system is currently under commercialization. So I'm very excited and hope that this system will soon be available to the end consumers. Okay. And we also applied this idea of incorporating users' aspirational preferences to the domain of podcast, where I develop an aspiration-informed podcast recommender. And we customize a commercial application and give it to 150 participants to use for a month. And in this field study, we conduct over 50 hours of one-by-one interview and communicate with participants on a daily basis. And we find that our system is able to encourage users to consume 35% more content that are aligned with their aspirations. In other words, these kinds of user-centric systems can really help people to make better content choices in the real world. And more details will be presented in my upcoming paper, and I'm happy to talk about this work offline. So during my PhD, I've developed many different recommendation algorithms for specific domains. And this makes me think whether we can generalize or adapt solutions that we develop for specific domains to others. And in order to do this, I built and release and maintain an open source library called OpenRec, which modularizes recommendation algorithms that are traditionally developed for specific domains so that it can be easily adapted to different application scenarios. And this library was published in Wisdom 2018 and is completely open source and free to use. And you can use this library to build new recommendation systems, reuse existing ones, and even for classroom and education purposes. And in fact, since this library was published 10 months ago, it has been externally, people have expressed significant interest in OpenRec, and it has been featured in the flagship industry conference built at Cornell Tech and attracted a full house of tutorial attendees as Rexis, which is one of the major research venue for recommendation system research. And there are already companies that deploy OpenRec in their production systems. And moving forward, my goal is to make OpenRec a go-to place for the recommendation system research. Okay, so, and in fact, the public has growing interest in the user-centric recommendation system, and my thesis research has recently been featured in this Wired article, the people trying to make internet recommendations less toxic. Although I think the title is a little exaggerated, but it's cool to find that the public's finally interested in the utility of the recommendation systems. Cool. So in summary, in this talk, I've shown you 2 example techniques that can enable user-centric recommendation systems. And at last, I want to just spend maybe 2 to 3 minutes to briefly mention about my future research plans. So moving forward, I want to take my expertise in recommendation systems and generalize it to personalized intelligent algorithms and systems that are becoming more and more common and pervasive in people's daily lives. And this idea of personalized intelligence is to personalize not only online recommendation systems, but also smart devices, agents, and personal robots in the physical world. And for the interest of time, I'm going to just give you two example research threads as examples. So the first thread is about developing personalization methods and algorithms for intelligent assistants, such as Amazon Alexa, Apple Siri, and Google Assistants. And these systems require us to think about a different paradigm of how can we do personalization in these kind of devices. Specifically, these systems need to do personalization with sporadic interactions with users. And in other words, these systems need to handle the cold start problem in a very smart way. And during my PhD, I've worked on this idea of immersive recommendation that tackles the cold start problem by profiling users across broader data sources from multiple platforms. And such a cross-platform personalization, I think, is very promising in enable immersive personal assistants. Also, these systems are inherently interactive. And these interactive systems are very different from the human-in-the-loop systems that people develop for collecting labels for machine learning algorithms. And we need to optimize the feedback loop for understanding and profiling users, as I talked about earlier in the Yummy work that we developed. And also, when building these systems, I think it's very important to build in privacy-aware into the algorithms and systems that we develop. And in this thread, I have some prior work that gives users the control of their data in recommendation systems, and I would like to continue pursuing in the future. And in addition to developing new personalization algorithms, I think it's equally important to understand and mitigate the unintended consequences of personalization. So there's no doubt that personalization has a profound impact on people, but oftentimes, many of these impacts are not intended when designing these systems initially. For example, does these systems reduce our productivity and creativity? Does it introduce bias and unfairness into our society? And does it alter our views and values? And to answer these questions, I think there are a tremendous opportunity in applying counterfactual reasoning and causal inference on the large-scale behavior data that people collected, as well as conducting carefully designed field experiments and building simulation environments to simulate user behavior. And just give you a very quick example. So I have an ongoing research that look at people's YouTube watch history from Google Takeout to understand how recommendation systems modulate people's aspired choices over time. So with this, I would like to thank my collaborators, advisors in Cornell and in industry, as well as over a dozen students that I mentored. So without them, my work would not be possible. So with this, I'm happy to take any questions.